Okay, so this next one is going to seem really easy at the outset, and the answer is actually easy to remember. But the argument from first principles is actually a little sophisticated, and it does require the third law, Newton's third law. So, assuming no friction, what is the acceleration of the system in terms of mass A, mass B, mass C, and the external force? So we have some external force here. It's provided by something that's pulling these three sleds. And we're imagining that there's no friction, so there's maybe these sleds are moving across ice or something like that. And each of the sleds has a mass, and they're attached to each other by strings, by tension forces. And the sort of naive answer, which is correct, but the answer that you would just kind of think has to be true, would be that it would be MA plus MB plus MC times A is equal to F external, right? And you would just solve for A by dividing by these three. And that's true, but I didn't really tell you that F equals MA applies to systems. I told you it applies to masses, right? And so what we have to kind of determine is, does the system act as one large mass when it's coupled together by these strings? And the answer is going to turn out to be yes. So the final answer, which I will justify, is going to be that it's just X external divided by MA plus MB plus MC. And the sort of way I'm going to record this as a lesson for you is that the acceleration of a system is the effective mass of is the force that exerted on that system divided by the system's effective mass, whatever that effective mass is found out to be. So, to analyze this system, I need to think about the three objects, A, B, and C. And so actually let me go back here. So there are forces acting on these, okay? A experiences a force to the right exerted on it by B. B experiences two forces, a force from A and a force from C. And finally, C experiences two forces, a force from B and force external. Now we have to distinguish these two from each other because they're not going to be the same force, even though I'm using the same label. So let's make the notation a little more sophisticated. So we're going to say, let me just erase this. We're going to say that this is the force that B exerts on A, like that. Then there's going to be the force that A exerts on B, and the force that C exerts on B. And finally, we're going to have the force that C exerts on, that B exerts on C, and we're going to have the external force. Okay. So I have my free body diagrams. The free body diagram for A is just a vector which points to the right, which is the force that B exerts on A. The free body diagram for B is just two vectors, one which points to the left and one which points to the right, the force that A exerts on B and the force that C exerts on B. And the free body diagram for C is the force that B exerts on C and the external force. If we consider forces which point to the right to be positive and forces which point to the left to be negative, I can compute the sum of forces for each of these. So the sum of the forces acting on A, the sum of the forces acting on B, and the sum of the forces acting on C. This will be FBA. This will be FCB minus FAB. And this will be F external minus F BC. Okay. So I can set up a system of equations using Newton's law that F equals the net force is ma. And so I can get for sled A, FBA equals the mass of A times the acceleration of A. For sled B, F of CB minus F of AB equals mass of B times the acceleration of B. And F of external minus F of BC equals the mass of C times the acceleration of C. Okay, this is all for Newton's second law. From Newton's third law, I have that the action-reaction forces have to have the same magnitudes, but opposite directions. So the third law gives me the following equations. F of BA equals F of AB, right? Because that's an action-reaction pair. This guy and this guy is an action-reaction pair. Same magnitude, opposite directions. And F of CB equals F of BC. Okay, that's good. But I have another fact, which is kinematical in nature. This is from kinematics. And that's the fact that all of these sleds are attached by ropes, okay? And the ropes can't extend, and they're not going slack. So because the ropes are taut and not able to extend further, the rightmost sled, if it moves to the right, the middle sled has to move because the rope can't get longer. And the leftmost sled has to move also in lockstep because that rope can't get longer. And so because the ropes are inextensible ropes, because they're inextensible, all the accelerations have to be the same. Okay. For one of the accelerations to be different would mean that one of the ropes is either becoming slack or that it's stretching, elongating. We're disallowing an elongating rope, so it's not like a rope made of putty or something like that. And we're pulling the system to the right, so there's no opportunity for the ropes to go slack. So now we can try to solve the system. And so what I'm going to do is I'm going to define this to be A. And I am then going to add my equations together. So I have equation 1, 2, and 3. So if I add those three equations together, what equation do I get? Well, going back, what do I have? I'd have F of BA plus F of CB minus F of AB plus F external minus F of BC. And that's going to equal MAAA plus MBAB plus MCAC. Now, Newton's third law tells me that this is the same as that, and that this is the same as that. So those guys cancel each other out. And so on the left-hand side, I'm left with just the external force. All the internal forces canceled and we're balanced. And on the right-hand side, because all the accelerations are the same, that's just an A, that's just an A, that's just an A, I can factor out that A, which is in common, and I'm left with MA plus MB plus MC, which is just the total mass of the system. Okay. And this is actually, the relationship that most students kind of just assume because they know Newton's second law, and it should be reassuring that we came to that relationship. But the reason I'm explicitly working this out here is because you do need to know how Newton's third law works. And Newton's third law is what's telling us that this guy and this guy are able to cancel, that those internal forces will ultimately cancel when you sum over the entire system. So that's what I meant in the first lecture when I said all the internal forces in a system that is closed will cancel out. So the system accelerates. It accelerates because of a force which is external to the system, and the forces end up adding together. And the masses end up adding together, I mean. And so now the acceleration is just that external force divided by ma plus mb plus mc. If I wanted to go back and find some of these internal forces, I could substitute this acceleration into the appropriate equations. So for instance, if I want to know FBA, well, I know ma and I know the acceleration now, so I can solve for this by just doing an appropriate substitution. Similarly, once I know this guy, I can substitute him there. I can substitute for him and him because I know the acceleration and I know the mass, and that would give me this guy. And finally, this guy is him, and I know that mass, and I know that acceleration, and so, but I also know the external force, so at that point I would actually already know everything in the whole system. So if you're so inclined, you can go back with specific numbers and try to work that out and find out all the internal forces in a system. Okay, that is this lecture completed.